Day 24, page 654, number 1. Here's a good conceptual problem. We have a negative charge that's being moved from a 0 volt potential, 0 joules per coulomb, to a location, let's say it's the whole way. It doesn't say that's the whole way, but you're going to another location where you're going to have a potential of 100 joules per coulomb. I'm doing this all by convention. We have the positive plate being the 100 joules per coulomb of potential. The charge would easily do this on its own. It wouldn't take any work on my part or the mover's part to actually do this work. In fact, we are going to be, in a sense, doing negative work. I'll talk about that more later, to keep the particle from speeding up, turning the potential energy it has over there near the negative plate into kinetic energy on the other side. So that's the work we'll be doing. In other words, we'll be applying a force to the right while the particle is moving to the left. So let's figure this out. Bottom line, one of the best equations to use that I'm looking at here is delta V equals delta U over Q. And we also know that delta V equals ED. But I won't be using the delta V equals ED. I'm going to be using just this delta V equals delta U over Q. I know the delta V for this particular particle will be positive 100 because I'm going from 0 to 100 volts. So plugging into that, I'm going to get 100 volt potential difference equals the delta U over, well, Q is negative 25 nano, which is times 10 to the negative 9th coulombs. So delta U will be negative 2.5 times 10 to the negative 6th joules. Alright, so it will lose 2.5 microjoules of potential energy because that negative charge has put more potential energy by the negative plate than by the positive plate, opposite of what would happen to a positive charge. So it lost potential energy, but it didn't gain any kinetic energy. So bottom line is the worker did negative work. In other words, W, work energy theorem, the work done, or delta W, if you want to call it delta W, the change in work, or the work, is negative 22.5 times 10 to the negative 6 joules. We did negative work. Another way to think about it actually would be, if you look at the work equation, work equals F dot D, which is work equals F d cosine theta. You're going to be applying a force, which we don't need to figure out here, the distance, which was given but we really don't need to use. But I'll look at the cosine of theta. As the particle moves to the left, the force that we're applying to keep it from speeding up is to the right, so it'll be a cosine of 180. And if you remember that or check it out on your calculator, the cosine of 180 is negative. So the work done here just by plugging in there will be a negative quantity. You're doing negative work. You're not allowing the particle to pick up its kinetic energy. You're just robbing it of its potential energy.